Hello, my name is Lutfi Al-Sharif. I'm from the University of Jordan. My co-author is Mohammed Al-Adam, who's not going to be unfortunately with us today. I will be talking about the different methods for comparing and designing elevated traffic analysis and design. There are 4 methods which I'm going to present today. I'm from the University of Jordan, the Mechatronics Engineering Department. So let us start by looking at the contents of this presentation. I'm going to give some introductory concepts. Then I'll talk about some of the basics, some of the elevator design basics. Then we'll talk about the first 2 methods of calculation. So as you will see, the 4 methods are split into 2 generic groups: calculation methods and simulation methods. And under calculation methods, there are 2 methods. And under simulation methods, there are also 2 methods. I will finish up by comparing the methods, the various methods, and then we'll make some conclusions. So let's start talking about some introductory concepts. In general, we use models in everyday life. So we use models in engineering, we use models in economics, in sociology. And the models are of different types. They have they differ in their number of parameters. So generally I would classify models either deterministic or stochastic is also another term for probabilistic or random. Models can also be static or dynamic, and they can also be discrete versus continuous. This is just a general introduction to the different types of models before we start talking about elevators and elevator traffic design. So when we say deterministic versus stochastic, deterministic model is actually a model in which events are known in exactly which way they will happen. We know that in advance, while a stochastic model is a model where things happen randomly. And in reality, we probably do need to model stochastic processes because we need to have a more realistic view of how the model will run and how these random effects will have on the model. So as I said, it's more realistic to simulate them in a random way. While deterministic models are well known in advance, we know exactly what's going to happen. But most things in life are not deterministic. They're probably nearer to a stochastic model. The second criteria by which we distinguish models is static versus dynamic. And when we look at a static model, we're only concentrating on the steady state. We are waiting until the system gets to a steady state, and we're just evaluating that final outcome. However, when we look at the dynamics of a system or a dynamic model of a system, we are interested in the changes. We are interested in how the system is changing from one state to another. It's more difficult to evaluate the dynamics of systems, but in many cases we are interested in the dynamic changes that happen within the system. Basically, we would say we are interested in a transient response rather than just a steady state. And the third way in which we can actually classify models is either continuous or discrete. And when we look at a continuous system, we are looking at variables that change continuously. A speed of a motor, for example, that is a continuous process whereby which the speed is changing continuously. The position, for example, of an elevator, or the level of fluid in a tank, all of these are continuous variables, and we have to model them in a continuous system. However, we can look sometimes at systems in a discrete way, in a discrete fashion, by which we are looking at different points in time where things are happening. So, for example, a customer is arriving for service at a bank, and we can look at specific points in that process. We're not interested in what happens in between. So the instant at which a customer arrives, that is a point in time which we're interested in. That is a discrete point. When he finishes or she finishes and leaves, that's another discrete point. So we can simplify things sometimes if we're only interested in specific points in time, and that would be a discrete system. Analogue computers are a very interesting example of how we used to model continuous systems. Analogue computers existed long before what we know today as PCs or laptops and discrete computers or digital computers, and they used to be used for modeling continuous systems. This is an interesting view of an analog computer that it's used for teaching, but can also be used to model continuous systems, especially in mechanical and electrical systems. We can model a continuous system using an analog computer. It's just introducing the concept or emphasizing the concept that some systems are continuous in nature. So having introduced that introductory concept about the types of models, I need to just talk a bit about elevator traffic design basics before delving into the 4 different methods which are the topic of this presentation today. So in elevator traffic design basics, if we actually look at how designers design elevator systems today, how they actually come to select the vertical transportation system for a specific building, we find that actually the final answer that the designer usually wants to arrive at is finding a suitable number of elevators and their speed and capacity. And the way usually the designer will go about doing that, the classical way, is to find the round trip time. And the round trip time is the time taken by an elevator to do a complete round trip around the building, usually under incoming traffic conditions in the morning up peak. And that would be like a cycle time for the elevator, and this is what we usually refer to as the round trip time, or the RTT. Now, the interval is also an important parameter because it represents the quality of service, and it's defined as the time between successive arrivals of elevators at the main entrance. So if a passenger arrives at the main entrance and is waiting an elevator, the maximum time that he or she would wait between the departure of an elevator and the departure of the following elevator is called the interval, and it's highly correlated with the waiting time that that passenger would wait. So having calculated the round trip time, then the designer would actually use that round trip time to calculate the required number of elevators. So having had the value, the round trip time is then divided by the required interval, and as I said before, the required interval is an indication of the quality of service, and that interval then is that number that results from dividing the round trip time by the required interval gives us the necessary number of elevators. That is the classical method of design that has been used so far for calculating the required number of elevators. Now, that approach is really based on calculation, and the reason I use the term calculation is because we calculated the round trip time rather than simulated it, and once we got the value for the round trip time, we divided by the required interval and arrived at the necessary number of elevators. And the necessary number of elevators, obviously, for obvious reasons, has to be an integer. It has to be a whole number. Now, there is an alternative approach which has started to be used in the last 15 or 20 years, which is simulation, by which we simulate the lift system. We let it run through as if we're looking at a real system, but obviously we're simulating it on a PC or a laptop, and we run it in order to find the average waiting time and the average traveling time. So here we're looking at more passenger-related parameters like the waiting time and the traveling time. And then obviously many people would use a hybrid approach between these two, so that they might start by calculating the round trip time, getting a feel for the required number of elevators, and then using a simulation approach to actually get a feel for the average waiting time, average traveling time. And probably what they could do as well, they could actually fine-tune the system, maybe change the speed, change the number of elevators in order to achieve the average waiting time or the average traveling time that they desire. So I guess in reality, most designers would actually probably use a mixed approach. They would start with calculation to get a feel for the required number of elevators, their speed and capacity, and then they would start refining that by the use of simulation, especially that the control algorithm would have an effect on the average waiting time and average traveling time, but really the control algorithm is not something we can actually easily introduce into the calculation and the calculation of the round trip time. So this final step would be a fine-tuning to see the effect of the control algorithm on the required average waiting time and average traveling time. So as I said in the previous slide, it's possible to have that hybrid approach, and this is probably what actually most designers would use. They go for the first step, the calculation, to get a rough solution, and then the simulation to refine that answer. So now we proceed to the core of this presentation, which is we want to look at both of those, both of these generic tools, calculation and simulation, and within each one of those we're going to look at the two methods. Within calculation we have two methods, and within simulation we have two methods. So we start now by looking at the first part of calculation, which is analytical equation-based methods. Basically, this is where we have a formula, and we use that formula to carry out a calculation to calculate the round-trip time. And what we are getting the value of a variable, or the expected value of a variable, which in this case would be the round-trip time. Obviously, we need to have these formulae to hand, or if they don't exist, we need to actually develop them or derive these formulae or equation to get the average of the variable. And in most cases, that variable will be the round-trip time, although it is known that we can now derive equations to do more advanced things, like maybe calculate the average waiting time and average traveling time. In some cases, we could actually look for the standard deviation, but in most cases it is actually the average value of that variable. So we get the value that results is the average value of round-trip time. But the problem obviously is that as the system gets more complicated, developing these formulae becomes very, very difficult. It is possible for simple cases, but gets further and further complicated as we require more variable. And also, specifically, calculation becomes very complicated when we have these different random input variables become dependent. Input variables, random input variables include things like the passenger origins, where they come from, the passenger destinations, the numbers of passengers. And as we have more of those random variables, and as they become dependent as well, then calculation methods start to become very, very unwieldy and very difficult to derive. What I'm going to show you now, I'm going to show you the basics of how calculation methods started, what equations they were based on, and what assumptions they made. And as you will see, once we calculate the round-trip time, then we can divide that by the required interval, and we can then find the required number of elevators. And if you look here, for example, you would see these three equations, very widely used, they've been around for a long time, and these are the three classical equations for the basis for calculating the round-trip time. The first equation shows us how to calculate the round-trip time, which I've referred to, or I've denoted here as tau. The second equation tells us about the expected number of stops, and the third equation tells us about the highest reversal floor. Combining all these three equations, we can arrive at a value for the round-trip time. But the problem is there are so many assumptions that these three equations make that this is only true. These equations are only true for a limited number of cases. These three equations make around 10 assumptions, and they make these assumptions. So unless these 10 assumptions are true, you cannot use this round-trip time equation, or if you do use it, then you actually have an error in the calculation of the round-trip time. As I said, as things get more complicated, then analytical methods grind to a halt. It becomes very, very difficult to use them as a calculation tool. And in these cases, we would then have to move to the next tool of calculation, which is called Monte Carlo Simulation. It becomes quite a powerful tool because then we don't have to make these 10 assumptions. We can actually remove one assumption after the second, and we can still use the Monte Carlo simulation to do these calculations. So we now move on to the next tool, which is next tool in the calculation, which is the Monte Carlo simulation. There is a bit of a misnomer here. It is called Monte Carlo simulation, but in fact we are using it here as a calculation tool. So we are still using it just to arrive at an expected value for the round-trip time. Where does it originate from? Well, Monte Carlo simulation, it was coined in the 1940s by three scientists who were working on the on a project in Los Alamos, John Von Neumann, Stanislaw Ulam, and Nicholas Metropolis. They were working on the Manhattan project in the Los Alamos National Laboratory. And it is claimed that it was named after Monte Carlo, where Ulam's uncle would often gamble away his money, and hence the name Monte Carlo. It has so many applications today in various areas, in finance, it allows us to evaluate an investment, or the value of an investment, or the value of a company. In computational biology, it can actually allow us to play games, outperforming previous algorithms. It allows us to do optimization, numerical integration. In engineering, it's widely used in engineering, in various areas in engineering. And I'm going to show you an interesting example which is much nearer to everyday life, which is the value of pi. Pi is actually the natural ratio between the circumference of a circle and its diameter. And pi is not actually a rational number. It's a number that has so many decimal places. And this is a very, very interesting example of how we can use Monte Carlo simulation to calculate the value of pi. If you look in the example here, we have a square, and a quarter of a circle is drawn there. And in fact, we could use this method if we had the large number of grains of rice. We could just start throwing them on this square piece of cardboard, and we count the grains of rice after doing it for a long time that fall within the quarter of a circle, and if we divide them by the total number of grains of rice, that would be the value of pi divided by 4. So if you multiply that value by 4, we get actually the value of pi in a very, very simple method. It's a very, very simple, very intuitive example of how Monte Carlo simulation can be used in solving a very simple mathematical problem. The same way we can, for example, if we were asked the question, what is the probability of getting heads or tails after flipping a coin, then intuitively we know that is half, but we can actually in fact use Monte Carlo simulation to arrive at a mathematical or a numerical value that answers that. Or, for example, again, if we were asked about the probability of getting a 1 on a pair of dice, we can use Excel, for example, is a good tool to actually show us some of those results. And all we need to do is keep on repeating that experiment. That's what we refer to it. We refer to it as an experiment or a trial, and we keep on repeating that trial a large number of times, 10,000, 100,000, 200,000 times, and we count the number of times we had heads, divide them by the total number of trials, and that number will start approaching half in the case of flipping a coin. Or, for example, if we were looking at the probability of getting a number 2 on a dice, then that would start approaching 1/6 in the same way. I'm not going to show you the Excel example now, but you can easily do that and have a look at the results that you get from it. Obviously, you would say, why would I need Monte Carlo simulation to solve a problem which is clearly intuitive, like, for example, the probability of getting heads or tails? That is true for a simple example, but as things become more and more complicated, then you will see that analytical methods become very, very difficult to solve. In this case, we only have a small number of input random variables. They also have a simple probability. We know that they're equally likely. 1, 2, 3, 4, 5, and 6 are equally likely. And most importantly, the two inputs are decoupled. So there is no dependence between the first throw of a pair of dice and the second throw. Once we start having more inputs and that they become interdependent, then that becomes more and more of a problem. And that's why in many engineering problems where we have a large number of inputs, Monte Carlo simulation becomes ideal for calculating the value of a random variable. So what is the benefit of using Monte Carlo simulation in elevated traffic analysis? You remember we mentioned the 10 assumptions that the classical set of equations assume. Some of these assumptions are that we only have a single entrance. The other assumption is we have equal floor populations. We have equal floor heights. We are assuming as well that the rated speed is attained in one floor journey, and we're assuming, for example, that we have a constant arrival process. As soon as we start deviating from any of those 10 assumptions, the equations become very, very complicated. But if we use Monte Carlo simulation, we don't have to worry about any of those special conditions. If any of those special conditions do not exist, we can still use Monte Carlo simulation easily to calculate the value of the round trip time. I'm going to show you the structure of a model which was built to support this. The model was called MaxiTAD, Monte Carlo Simulation, Elevated Traffic Analysis and Design. And the model has 3 main components. There is what is called the transition matrix generator, I'll talk about in a minute. There's a random scenario parameter generator, and there's a deterministic calculator. The transition matrix, basically, it's a matrix that tells me how long it is going to take me to travel from one floor to the next. And it basically uses the basic parameters about the building in terms of distance, the distance between one floor and the next, the number of floors, obviously, what rated speed am I using for the elevator, what rated acceleration, and what rated jerk. And it uses a number of equations to calculate the time needed to travel between one floor and the next. Obviously, as you would expect, the time taken to travel from one floor, I, to another floor, J, is the same time taken to travel from J to I in reverse. And also intuitively you would expect that the time taken to travel from the floor to the same floor obviously is 0. We're not going to travel from the floor back to the same floor again. In going back looking at the model again, the RSPG is actually at the heart of the model. This is the random scenario parameter generator. Every time we do a trial, we are generating what is called a scenario. We use probability density functions to generate the random variables, and basically the random variables are the origin of the passengers and their destination. Where does every passenger come from? That's a random variable. Where does every passenger go to? That's another random variable. And once we know where every passenger is coming from and where he or she is going to, we end up, if you see, you can see this diagram which represents the building, and if you look at the building, you can see that there's an entrance, what I've called denoted as 0, and there's a number of basements or sub-basements or multiple entrances, and that's where traffic originates. And there are probabilities, different probabilities for how passengers arrive at these arrival floors. Then we also have destination floors, which are numbered here, in this case from 1 to n, and this is where passengers are heading to. And if we start with an incoming traffic only, this is where passengers arrive into the building. This is what happens, for example, in the morning when people are arriving at an office building, going to their desks. They will arrive at the floors from 0, B1, B2, MB, and they will then proceed to one of the upper floors from 1 to n, in accordance with a certain distribution, probability distribution, and the probability distribution is predefined for this building because we know how people arrive at the basements and the entrances, and we know the populations of the upper floors, and that basically defines the probabilities of how passengers will behave. And let's take a simple scenario. On this graph, I've drawn time, which is the x-axis, and I've drawn the number of floors up here. And you will see this is where the door opens. Passengers will enter the car. This is where the door closes. The lift then proceeds to the first destination, which was selected by a passenger. The doors open again. The passenger leaves. The doors close. And then the lift proceeds to the other floors until the elevator finishes and delivers the last set of passengers and returns back to the ground floor or the entrance. And the time between that starting and finishing is what we would denote as the round trip time. This is one scenario. Obviously, we need to repeat this scenario. We need to repeat this a large number of times in order to get an average value for the round trip time. So the two main random variables are origins and destinations, and we can sample those origins and destinations by producing what is called a probability density function, a PDF, and a cumulative distribution function. This is just the mechanism by which we can actually generate these random arrivals and random destinations. So if we look, for example, at the arrivals, we use what I've denoted here as the probability of arrival from floor I or entrance I, and that would give me a number of probabilities for the various floors. Or if I'm looking at the destinations, I'm taking the floor population into consideration, which I've denoted as UI, where UI is the population of the ith floor divided by the total population of the building, and that would give me a feeling for how probable it is for a passenger to go to the ith floor, or in this case, how probable it is for the passenger to arrive from the ith floor. If we convert this into a cumulative distribution function, then all I need to do is to generate an arrival or a destination. It's generate a random number from 0 to 1. You can do that on your calculator easily. And once you have that number, you drop the resulting number here, and that gives you a destination or an arrival. It just shows you the mechanism by which you can actually generate a random number. This is the transition matrix, and the transition matrix tells me how long it will take based on the speed, acceleration, jerk, and distance between one floor and the next to travel between these two floors. As you would expect, going from one floor to the same floor will give me a 0, so the diagonal of this matrix has all zeros, and then going from one floor, from MB to MB minus 1, is the same value as going from MB minus 1 to MB. So this is just a matrix which we prepare in advance. It's a transition matrix, and it tells me how long it is going to take me to go from one floor to the next. Having prepared the transition matrix, we're going to look now at the various blocks within a Monte Carlo simulator. At the core of it is the random scenario parameter generator. And then we feed that with the number of floors above the main terminal. We also feed it with the destination probabilities, where the probability of going to a certain floor. We have the number of passengers in a car, the number of basements, or the number of entrances. So all of these are inputs which are going into the random scenario parameter generator, and the arrival probabilities. Then the random scenario parameter generator will generate one scenario or one trial, and from that we have a scenario which is described by the arrival stops, where are passengers arriving from and where are they going to. So we have a full trial now which we can calculate the round trip time for, and to calculate the round trip time we need to have the travel time matrix which we saw in the previous slide, which is based on the distance, the velocity, the rated velocity or speed of the elevator, the acceleration and the jerk. By combining those with the arrival stops and the destination stops, we can then use the deterministic calculator to calculate the round trip time based on the number of passengers in the car and the passenger boarding times. And that would give us now one value out of one trial or one scenario for the round trip time. Obviously that is just one value, and we need to repeat that a large number of times, so we probably have to repeat it for 10,000, 100,000, a million times in order to get the average of all of those values, and that will actually start approaching the true value of the round trip time. So as I said, this has been implemented in a piece of software called MaxITAD, which is short for Monte Carlo Simulation, Elevator Traffic Analysis and Design. And it is a tool for calculating the round trip time. As a reminder, as I said before, although it is called Monte Carlo Simulation, it is really used in this context as a calculation tool rather than a simulation tool. This just shows you the graphical user interface for entering the parameters for the building, the occupant floors, exit entrance floors, the various arrival and departure probabilities, and from that then the software will give us some of the results for this building. One of the important issues in Monte Carlo simulation is how fast does it converge, and convergence is actually an important issue because it tells us how many scenarios, how many trials do I need to run in order to get to the correct value of the round trip time. But how long does that take me as well in processing time on a PC or a laptop? We need to select a suitable number of trials so that we converge to the correct value, but it doesn't take us very long to get to that convergence. So, for example, we can set a convergence criteria by which we say, for example, if there's a change of less than 0.01 of a second in the round trip time, then it means that we have arrived, we have converged. There's no point in doing more trials. For example, 100,000 runs is sufficient. It might sound a lot, 100,000 might sound a lot, but in fact, with the power of today's PCs and computers, that will hardly take a couple of seconds to run. And this chart shows you, for example, how the tool is converging as we increase the number of trials. Please notice that the scale here, the x-axis, is actually a logarithmic scale, so we are multiplying by 10 each time, and you can see as we approach 100,000 or a million trials, all the values are superimposed on top of each other, showing that we actually have achieved good conversions after that number of trials. Also here, for example, it shows a trade-off between the number of trials and the deviation percentage from the mean, and you can see we're achieving excellent values by the time we get to around 100,000 or a million trials. We're getting good percentage or good error values in lower than 0.1%. So as I said in the previous slide, it's really a compromise between spending too much time doing these trials and getting a reasonably good value. And it seems that around 100,000 runs seems to be a good number to aim for in terms of trials. For example, this will take around 7 seconds on an average laptop, and it provides an accuracy of around 0.1%. And this is shown in tabular format, and you can see this is, for example, for the average traveling time, and it's taking a bit longer because that takes more time to calculate. So now we've finished the calculation. We've looked at the two tools of calculation, which were analytical equation-based methods and Monte Carlo simulation. But as I said, most designers today still use calculation to start with, and then they use simulation to fine-tune. So I'm going to talk about the two simulation tools available to us today, and the first one of those is the Discrete-Event Simulation. Please remember that I did mention at the beginning when I was talking about different types of models that there are continuous models and discrete models. So Discrete-Event Simulation exploits the fact that systems can be discrete, and where a system is discrete, it will be ideal to apply Discrete-Event Simulation to that system. So Discrete-Event Simulation is a simulation tool. It shows us the change in the state of the system at various points during the simulation. And obviously, the nature of the simulated system must be discrete for this tool to work. And in effect, what happens is that the simulator will start jumping from one point to the next point of interest in the operation of the system. We can't really use discrete event simulation to simulate continuous systems. Some people will argue that they can, but it's probably not in the nature of it. A good example of a discrete event simulator is the building traffic simulator, which is developed by Connie Corporation, and it utilizes discrete event simulation. So a discrete event simulation, this is the approach used in discrete event simulation. It uses time increments, but the time increments are variable. They coincide with specific points of interest in the simulation of the system. And it only updates the system when something interesting happens. And so this is much more intuitive. In an elevator, if we think of an elevator, we do have clear points where an event does happen and is of interest. Let's take a simple example here from a cashier or a server serving a client. If we look at the time, for example, we started at 9 o'clock. Then something interesting happened at 1 minute past 9 and 25 seconds, and a customer arrived. So we only simulate that point in time. We're only interested in that point in time. And then if we know how long that customer finished, then we only record the point at which he finished. You can see that all the time in between, we're not really interested in the detail that happened in between. This shows that this method is very efficient. We've actually just concentrated on these points of interest between the arrival of the passenger and the passenger being served and leaving. This shows a classical event loop for a discrete event simulator. And it effectively, what it does is shows the flow chart. It sorts the events in an ascending list. It looks at the most imminent event, and it effectively, the term is used here is to pop it, take it out. It updates the simulation time, and then it informs all the entities within the software about this event, because they may be effect on other entities and other events in the simulation. And then it looks at the next event, which will happen chronologically. This was also implemented in another tool at the University of Jordan called LFSIM, standing for Elevator Simulator, and it's a discrete event simulation tool to simulate passengers arriving in a lift system. It was written in C++ with a GUI, a graphical user interface. It also has a scripting system, because what it can do, it can allow users to script or write a script describing how a group control algorithm works. And if you remember, this is one of the advantages of simulation, is that it allows us to evaluate group control algorithms, something that is very, very difficult to do under calculation, whether it is Monte Carlo simulation or equation-based. So in general, once the designer gets to the stage where he or she wants to evaluate the effect of the group controller on the design, then he will usually or she will usually use a simulator, whether it be a discrete event simulator or other types of simulation. This software has around 6,000 lines of code. So now we move to the second tool within simulation, which is called time slice simulation. And these are the main two means of simulation that are used nowadays. We either use discrete event simulation or time slice simulation. And if you remember, we said discrete event simulation can only really be used for discrete events or discrete systems. So in an elevator, if all we're interested in is the arrival of a passenger, the departure of the passenger, serving of a passenger, then we can concentrate on discrete event simulation. But as we will see now, there are situations where we do need time slice simulation, because time slice simulation will allow us to also simulate continuous systems and continuous events. Under time slice simulation, as you would imagine from the name time slice, we are slicing the time of the simulation into fixed increments, and each of these increments is called the time slice, and it's probably going to be something like 10 milliseconds or 1 millisecond, for example, and these time slices needs to be small enough in order to allow us to capture everything that happens. But as you will see here, the increments are fixed in size. And then the system state is calculated at the end of every time slice, whether something interesting has happened or not. And that's why a time slice simulator is ideal for simulating continuous systems as well as discrete systems if we wish to do so. And if we go back to our example with the receptionist and the customer, we can see, for example, we start at time 9 o'clock, and 1 minute past 9 nothing has happened, but still we actually updated the system. 2 minutes past 9, in fact the passenger arrived at 9 hours 1 minute and 25 seconds. But obviously, because we're only revisiting the system every minute, that will be a disadvantage of the system, by which we actually don't record the exact time of arrival of the passenger. If we want to be more precise, we have to select a smaller time slice. 3 minutes past 9 o'clock, the passenger was still being served, so nothing of interest has happened, so as we update the system, and 9 hours and 4 minutes, nothing had happened, but 5 minutes past 9, the passenger had actually departed within that time, which is 4 minutes past 9 and 40 seconds. So as you can see, we've had to update the system 5 or 6 times in this case, whether something new had happened or not, and then events that had happened in between were recorded either at the beginning of the time slice or the end of the time slice. Obviously, this example was given. It shows that a discrete event simulation would be suitable, and we don't need time slice simulation. But as you can imagine, if we wanted to use time slice simulation to simulate continuous events, then that would be the ideal application of time slice simulation. There is a software that exists. It's used by, it's implemented in a software called Elevate, which was developed by Dr. Peters of Peters Research, and it does utilize time slice simulation, and it does allow the mixing of discrete event systems and continuous event systems, by which, for example, if we had an energy model or a kinematic model and we wanted to simulate that as well as simulating the discrete events, we can do that within Elevate. So let's do a comparison now of the 4 methods that we've talked about. We're going to use 5 criteria for comparing the methods. So we look at simplicity, complexity, calculation time, ability to deal with continuous models, convergence to a final value, and ability to evaluate group control algorithms. So if we look at simplicity, obviously the most simple of the 4 methods is the equation-based method. You just have an equation, assuming it has been derived, and you pop in the values and you get an answer. However, obviously, if we want to derive a new equation, that is actually not very easy, and it takes a lot of effort and time to derive a new equation within the equation-based method. We can say that the time slice simulation is the most complex because it's taking a lot of time to process. It needs to keep on revisiting the system every time slice and updating it. If we take the second criteria, which is calculation time, obviously equation-based methods is still the fastest as well, because all we're doing, we're just calculating an equation. We have a number of variables we put into equation, and it gives us an answer. Monte Carlo method is probably slightly faster, but it does take some time to process until it gets a value. So we could say it takes 1 to 10 seconds, for example, to get an answer from a Monte Carlo simulator. Obviously, with the other methods, simulation tools will take longer to provide answers, understandably for obvious reasons. Dealing with continuous systems, we could argue that we could use time. The best method for dealing with continuous systems, as described earlier, was the time slice simulation method, and the time slice simulation method deals very well with continuous systems. It's the best method for doing that. For example, to take an example of that, if we have an elevator group control algorithm, we want to assess that at the same time as assessing, for example, vibration frequencies in an elevator and also capturing the energy consumed, then realistically the only tool that can be used is a time slice simulator. If we look at the next criteria, which is convergence, obviously an analytical equation is instantaneous. Obviously it gives us an immediate value. We can't talk about convergence because it's instantaneous. A Monte Carlo simulation takes around 10 seconds, probably in the worst cases, to converge, so that's probably acceptable. Convergence becomes more of an issue when we talk about simulation methods. If we really want to converge to a specific one value, then we need to take a large number of simulations, which can become time-consuming. Most people in simulation would accept an approximation rather than an exact value following convergence. Evaluation of group control algorithms. Some people have tried to use analytical equations to evaluate group control algorithms, but generally it is accepted that it can only be done using simulation. The only practical tool for evaluating group control algorithms is simulation. You could try to use Monte Carlo simulation and equations, but as I said, simulation is the only realistic tool for evaluating a group control algorithm. Repeatability is a problem in simulation, and as I said, because there's no convergence, so you really have to repeat this a large number of times in order to get one specific number which is repeatable. I've tried to summarize these 5 criteria. I'm not going to repeat them again, but the slide is there for someone who ever wants to refer back to it again. I've tried to summarize the 4 methods against the 5 criteria as a comparison. So having concluded the methods, the 4 methods, 2 under calculation, 2 under simulation, I'm just going to try to draw some conclusions from this presentation. So basically, as I said, there are 4 methods, 2 calculation tools, which are analytical-based calculation methods and Monte Carlo simulation, or we can use simulation tools, discrete-event simulation, which is suitable only for discrete events, or time-slice simulation, which is suitable for both continuous and discrete systems. Usage of each one of them depends on the complexity and the objectives. As I said, there's probably a hybrid approach which is used by designers where they start with calculation to get a rough answer or a ballpark figure, and then they move on to simulation to fine-tune the answer and then see the effect of the control algorithm and do maybe some what-if scenarios. If we're interested in convergence to one specific value, then calculation is the best tool. Either analytical equation-based calculation or Monte Carlo simulation are ideal tools to use if we want to converge to one specific value. We have to distinguish between transient behavior and steady-state behavior. Simulation tools will let us see how transient behavior takes place, how it moves, but calculation tools will let us know what the steady state we actually arrived at eventually. So simulation tools are ideal for capturing this transient behavior. As I said, simulation tools are also ideal for evaluating the effect of different group control algorithms on the design. If we want to use simulation systems, if we want to evaluate continuous systems, then time slice simulation must be used, as we can then simulate discrete events and so on, or we can look at speed, the change in speed, the change in energy consumption in systems. So this brings me to the end of this presentation. I hope you've enjoyed this and found it useful, and thank you very much for your attention.